June 1978, Cambridge, Massachusetts. William LeMessurier sat in his headquarters office, one of the nation's most celebrated structural engineers at the peak of his career. But that June, the phone rang with a question that would nearly destroy him. The young voice on the other end belonged to an architecture student working on a thesis about the Citicorp Center, the 59-story silver skyscraper that had become Manhattan's 7th tallest building just months after its completion. LeMessurier had designed the 25,000-ton steel skeleton beneath its distinctive slanted aluminum roof. He'd been praised in every major publication. His career was untouchable. That was about to change. The student asked about quartering winds that strike a building diagonally at its corners rather than hitting the flat sides head-on. Most skyscrapers are strongest at their corners, LeMessurier explained. So perpendicular winds blowing against the flat faces create the greatest stress. New York City building code only required calculations for perpendicular winds. He'd done those calculations. The building was safe. But as LeMessurier hung up the phone, something gnawed at him. He couldn't shake the question. So he pulled out his calculations and began checking his work, running the numbers one more time for quartering winds, just to be certain, just to prove the student wrong and put his mind at ease. What he discovered in those next few days would haunt him for the rest of his life. The student wasn't wrong. The building wasn't safe. And William LeMessurier was the only person in the world who knew that one of New York City's newest landmarks could collapse in the next strong storm, killing thousands of people in the most densely populated city in America. This is the story of how an engineering triumph became an engineering nightmare, how a man faced the choice between silence and professional suicide, how welders worked through the night in secret while a hurricane bore down on Manhattan, and how one of the worst disasters in American history was prevented by a decision that would either destroy or define the man who made it. The Citicorp Center, later renamed Citigroup Center, rises 279 meters above the streets of Midtown Manhattan at 601 Lexington Avenue. With its triangular roof inclined at 45 degrees, it immediately stands out against the city skyline. A really striking, unforgettable building. But what made it truly revolutionary wasn't the roof. It was the stilts. 4 massive columns, each 34 meters tall, holding the entire structure above the ground, not at the corners where you'd expect them, at the center of each side. This wasn't an aesthetic choice. It was necessity transformed into innovation. The northwest corner of the building site belonged to St. Peter's Lutheran Church, a modest Victorian structure that the congregation refused to abandon. The land was theirs. But the air rights above the church, those could be negotiated. So architect Hugh Stubbins and structural engineer William LeMessurier designed something unprecedented. They would put the entire skyscraper on stilts, positioned at the middle of each wall, allowing the building to cantilever over the church below. LeMessurier sketched the initial design on a napkin at a Greek restaurant. 4 offset columns, diagonal bracing running up the building's interior to transfer wind loads from the upper stories down to those 4 points of support. And at the very top, a 400-ton concrete block floating on pressurized oil bearings, the world's first tuned mass damper in a building. This mechanical device would shift its weight to counteract the building's natural swaying in the wind, keeping occupants comfortable during storms. It was brilliant. Unconventional. Elegant. The engineering press celebrated it as a masterpiece of structural innovation. When the building opened in 1977, LeMessurier became one of the most sought-after structural engineers in the world. But brilliance has a shadow side, and LeMessurier's design contained a flaw that wouldn't reveal itself until a student asked the right question. To understand what went wrong, you need to understand how buildings resist wind. When wind hits a rectangular building perpendicular to its face, it creates enormous pressure on that side and suction on the opposite side. The building tries to tip over like a domino. In a conventional design with columns at the corners, this load travels down through the corner columns directly to the foundation. Simple. Efficient. The building is braced at its natural strong points, where the structure is inherently most rigid. But Citicorp Center didn't have corner columns. Its columns were in the middle of each side, positioned where buildings are typically weakest. Every structural engineering textbook would tell you this violates basic principles. You don't put your support where the structure wants to bend. You put it where the structure is naturally strong. So LeMessurier had to redesign how buildings resist wind. He created a system of diagonal braces, massive steel chevrons running up the building's interior like enormous V's stacked on top of each other, 8 stories at a time. These weren't decorative. They were the building's primary defense against collapse. Each chevron was a steel lattice structure weighing tons, designed to catch wind loads from the upper floors and transfer them diagonally down and inward to those offset columns. The system was mathematically elegant. Wind hits the building's face. The force travels into the floor slabs. The floor slabs transfer it to the chevrons. The chevrons carry it down through the structure. The columns receive the load and push it into the foundation. Everything works together. Everything depends on every other thing. The system worked beautifully for perpendicular winds. Every calculation proved it. LeMessurier had used the best structural analysis methods available in the mid-1970s. He'd checked his numbers multiple times. The building code requirements were satisfied with comfortable margins of safety. LeMessurier had initially studied winds from all directions during his design work. He'd looked at quartering winds early on, but his analysis suggested they weren't the critical case. And the building code only required calculations for perpendicular winds anyway. So he focused his detailed work on that scenario. His confidence was justified. Perpendicular winds are typically the worst case for rectangular buildings. A structure designed to handle them usually handles everything else just fine. Usually, in May 1978, about a year after the Citicorp Center opened, LeMessurier was designing another building in Pittsburgh with similar diagonal wind braces. A potential contractor questioned why the design specified expensive welded joints instead of cheaper bolted connections. Welding created stronger joints, but it was slow and costly. Couldn't they use bolts like they'd done at Citicorp? LeMessurier paused. Like they'd done at Citicorp. He asked his office how the welding had gone at the Citicorp construction site. The answer changed everything. The joints hadn't been welded. The construction company had substituted bolted connections. LeMessurier felt the floor drop out from under him. Not immediately, not with the full horror of what it meant. But he felt something shift in his understanding of the building he'd designed. Someone at the construction site had looked at his specifications for full penetration welds, looked at the schedule, looked at the budget, and made a decision. Bolts would be faster. Bolts would be cheaper. Bolts met the building code requirements. From a practical construction standpoint, the substitution made perfect sense. Welding. Large structural connections is time-consuming. Each joint requires careful preparation. The surfaces must be cleaned and aligned precisely. The welding process itself is slow, with each pass adding layers of molten metal. The welds must cool properly. They must be inspected. Any defects mean starting over. In a project the size of Citicorp Center, substituting bolts for welds could save weeks of construction time and hundreds of thousands of dollars. And technically, it was acceptable. The building code didn't require welded joints. Bolted joints of the right size and configuration could meet code standards. The change didn't require approval from the structural engineer because it didn't violate any code provisions. LeMessurier hadn't been informed because there was no legal requirement to inform him. At first, LeMessurier wasn't alarmed. Bolted joints were weaker than welded joints, yes. Everyone in structural engineering knew that. But they were still plenty strong for perpendicular winds. The building had been designed with significant safety margins, built into every calculation. Those margins existed precisely for situations like this. Unexpected variations during construction that slightly reduced the structure's strength. The substitution might have reduced those margins from comfortable to merely adequate, but not dangerously so. Not for perpendicular winds, not for the loading case he'd spent months calculating. But the student's question kept nagging at him. Quartering winds, winds hitting the corners. Had he checked that case with bolted joints? He knew he hadn't. He'd checked it with welded joints during the initial design. The results had been acceptable. But that was years ago, when the design was still being developed. He'd concluded that quartering winds weren't critical and had focused his detailed calculations on perpendicular winds because that's what the code required and what normally governed design. But now he had bolted joints instead of welded joints. And that changed everything. When wind strikes a building at 45 degrees, hitting two adjacent faces simultaneously, it creates a completely different loading pattern. The force doesn't hit the flat side and transfer cleanly down through the bracing system in the nice, predictable way that perpendicular winds do. Instead, it twists the building slightly, creating torsional stresses that spiral through the structure. It puts unusual stresses on the joints where those diagonal chevrons connected to the building's frame, stresses that pull and twist simultaneously rather than simply pushing. In a building with corner columns, this twisting is easily resisted. The columns themselves are positioned at the building's corners, exactly where the torsional forces want to concentrate. The resistance is natural and automatic. But Citicorp Center didn't have corner columns. The building's corners were cantilevered, hanging in midair with no direct support. All the resistance to that twisting, all the force trying to spin the building on its axis, had to travel through those connections where the chevrons met the building's frame. Those joints were everything. LeMessurier sat down at his desk with his calculator, his structural analysis notes, and the building's construction drawings. He started with the basics: wind pressure equations, force distribution calculations, load paths through the chevron system. He ran the calculations for quartering winds with the original welded joints he'd specified in his design. The results were acceptable. Tight, but acceptable. The stresses were higher than for perpendicular winds. Definitely higher than he'd remembered from his initial studies years earlier, but still within the limits. The building could handle it with welded joints. The safety margin wasn't large, but it was there. Then he changed one variable in his calculations. He replaced the strength values for welded joints with the strength values for bolted joints. What he saw made his blood run cold. The numbers didn't just get worse. They got catastrophically worse. The bolted joints couldn't handle the stress from quartering winds. Not even close. Under the right wind conditions, specific combinations of direction and velocity that would hit the building at 45 degrees with enough force, the joints would fail. They wouldn't yield gradually, giving warning, allowing time for evacuation. They would fail suddenly, catastrophically, one after another in rapid succession. When the first joint failed, the load it had been carrying would redistribute to the adjacent joints. Those joints, already stressed near their limits, would be overloaded immediately. They would fail. More load would redistribute. More joints would fail. The cascading failure would race up the building faster than anyone could react. The chevrons would detach from the structure. The upper stories would lose their bracing, the only thing preventing them from toppling over. And with nothing to prevent it, with no resistance to the wind pushing sideways against 60 stories of steel and concrete, the building would collapse. Not might collapse. Would collapse. The mathematics were unambiguous. LeMessurier checked his calculations again. He went through every step. He looked for errors in his assumptions, mistakes in his math, any reason to believe he was wrong. He found none. The numbers were correct. The conclusion was unavoidable. Not in some theoretical 1,000-year storm, in winds that hit New York City regularly. LeMessurier pulled weather data for Manhattan. He calculated the wind velocity needed to compromise the building with its current bolted joints. Then he compared that number to historical storm patterns. A storm strong enough to topple Citicorp Center, he determined, hits New York City roughly once every 55 years. 55 years, within a human lifetime. Within his lifetime. But it got worse, much worse. The tuned mass damper on the roof only worked when it had power. Its sophisticated system of hydraulic pumps and sensors required continuous electricity to function. In a major storm, power outages were common. When the power failed, the damper couldn't counteract the building's swaying. The swaying would increase. The stresses on those joints would increase. LeMessurier ran the calculations again, this time assuming the tuned mass damper failed during a storm. The probability of collapse changed dramatically. With no damper, a storm strong enough to bring down Citicorp Center occurs in New York City once every 16 years. 16 years. He sat alone in his office with that number. 16 years. The building had opened in 1977. It was now 1978. By 1994, the building should statistically experience a storm strong enough to collapse it. By the end of the century, it was almost certain, and when it fell, it wouldn't fall alone. A 59-story building doesn't simply crumble in place. It would topple sideways, crashing into neighboring skyscrapers like a domino. The cascading destruction could level multiple city blocks. LeMessurier later wrote that there was a 100% probability of total collapse before the end of the century. When collapse occurred, he wrote, it would come suddenly, without warning, and would kill thousands of people. And he was the only person who knew. The building showed no visible signs of distress. No cracks appeared in the concrete. The structure behaved perfectly. Occupants went about their daily business on 22 floors of office space, completely unaware that they were working inside a ticking time bomb. The building's owners, Citicorp, had no idea. The architects didn't know. The construction company didn't know. City officials didn't know. Only William LeMessurier knew. And now he had to decide what to do about it. He considered his options in those dark July days. Each choice led somewhere terrible. He could say nothing. After all, no one else had discovered the problem. The building had been open for a year without incident. Thousands of people went to work there every day. Nobody had noticed anything wrong. No cracks appeared, no unusual sounds, no movement. The building behaved perfectly. Maybe it would stand for decades without facing a strong enough storm. Maybe the calculations were too conservative. Maybe his analysis was overly pessimistic. Maybe he'd made an error in his new calculations, not his original ones. If he stayed silent, his reputation remained intact. His career continued. His family's financial security wasn't threatened. His firm wouldn't face lawsuits. His insurance wouldn't be cancelled. He could retire in 20 years as one of America's most respected structural engineers. But people would die. Not today, not tomorrow, but eventually. Maybe in 5 years, when a hurricane made an unexpected turn toward the city. Maybe in 10 years, when a winter nor'easter stalled over Manhattan. Maybe next month. And when it happened, when that building came down and crushed the life out of everyone inside and everyone in the neighboring blocks, thousands of people would die because he chose to protect himself instead of them. He would know for the rest of his life, however long or short that might be, he would know that he let people die to save his career. Every morning he'd wake up knowing. Every time he looked at his children, he'd know. Every time someone mentioned the Citicorp Center, he'd know. And eventually, when the building fell, when the news showed the bodies being pulled from the rubble, when the death toll climbed into the thousands, he'd know that he could have prevented every single one of those deaths by making a phone call. Could he live with that? Some people could. Some people were capable of that kind of compartmentalization, that ability to separate professional mistakes from moral responsibility, to tell themselves that the fault belonged to someone else. The construction company that substituted bolts, the building inspectors who approved it, the code writers who didn't require enough analysis. Some people could rationalize it. William LeMessurier was not one of those people. He briefly considered suicide. In his later lectures about the crisis, when he spoke to engineering students about ethics and responsibility, LeMessurier admitted this. He didn't hide it. He didn't present himself as a hero who never wavered. The shame of having made such a catastrophic error, one that could kill thousands. The knowledge that his mistake endangered lives on such a massive scale. The impending destruction of everything he'd built in his career. Everything he'd worked toward. His reputation, his professional standing, his firm's survival. The thought crossed his mind that suicide might be an escape from the impossible situation he faced. But it would also be abandonment. If he killed himself, the secret might die with him, or someone else would discover it and handle it differently. And either way, he wouldn't be there to fix it. To use his knowledge of the building to guide the repairs, to take responsibility for his mistake. Suicide wasn't an escape, it was desertion. He knew what he had to do. It was the only choice that let him live with himself. He had to blow the whistle on himself. He had to tell the truth, accept the consequences, face whatever came, and do everything in his power to fix the building before disaster struck. On July 31st, 1978, 1 month after the student's phone call, 1 month of sleepless nights and racing thoughts and endless calculations, LeMessurier made the call that would either destroy his career or define it. He contacted the lawyer for the architectural firm that had hired him as structural consultant for the Citicorp Tower. He explained the situation. The lawyer contacted the firm's insurance company. The insurance company arranged an emergency meeting for the following day. In that meeting, LeMessurier laid out everything. The student's question, the discovery about bolted joints, the calculations for quartering winds, the 16-year storm cycle, the probability of catastrophic collapse, the potential for thousands of deaths. The room was silent when he finished. Then they brought in Leslie Robertson, one of the most respected structural engineers in the world, who had worked on the World Trade Center and had extensive experience in disaster management. Robertson reviewed LeMessurier's calculations independently. He confirmed the numbers. The building was at risk. The repairs needed to start immediately. Robertson brought another perspective to the discussion that terrified LeMessurier. Robertson had worked with the National Science Foundation and the National Research Council on teams that studied earthquakes, hurricanes, and floods. He understood disaster response at the highest levels, and his immediate assessment was sobering. When Citicorp's executives learned about this problem, Robertson predicted, they would evacuate the building within hours. The surrounding area would be cleared. The story would dominate every news outlet. Panic would spread through Manhattan. LeMessurier almost fainted. He hadn't wanted an evacuation. He believed the building was safe for occupancy under normal weather conditions, thanks to the tuned mass damper. As long as they could monitor the weather carefully and begin emergency evacuations only if a major storm approached, they could fix the building without terrifying the public or emptying Midtown Manhattan. But that was only possible if they could keep the crisis secret. Solving the engineering problem was straightforward. Heavy steel plates welded over the existing bolted joints would reinforce them, creating connections even stronger than the original welded design had specified. The welders could access the joints easily because Hugh Stubbins had insisted on putting the chevrons inside the building's skin rather than displaying them outside. With enough workers, enough materials, and enough time, they could fix the building. But time was the problem. It was the end of July. Hurricane season was approaching, and hurricanes were exactly the kind of storms that could knock out the building's power, disable the tuned mass damper, and create the wind conditions that would bring down the tower. LeMessurier was facing legal destruction, professional humiliation, probable bankruptcy, and the end of his career. But he was also facing a race against time to save thousands of lives. The next day, LeMessurier met with Citicorp's senior management. He expected the worst. He prepared for immediate evacuation, public panic, the collapse of his professional life. What happened instead stunned everyone in the room. Citicorp's leadership, led by Chairman Walter Wriston, listened to the entire explanation. They reviewed the calculations, they consulted with their own experts, and then they made a decision that would prove crucial to preventing disaster. They would authorize whatever repairs were necessary, provide whatever resources were required, and work to keep the situation quiet until the building was safe. No evacuation, no public announcement, no panic, just quiet, determined action to fix the problem before a storm could exploit it. The New York City Department of Buildings was brought into the discussion. City officials approved the emergency repair plan. They agreed that public notification would create more danger than it would prevent, because an evacuation would take weeks to plan and execute. But the repairs could be completed faster if workers could operate without interference. Everyone involved understood the stakes. If a major storm developed in the Atlantic and headed toward New York before the repairs were finished, they would have to implement emergency evacuations, potentially affecting tens of thousands of people in a 10-block radius. The New York Police Department developed contingency plans. The Red Cross placed 2,500 volunteers on standby. 3 different weather services were retained to provide 24-hour monitoring of every weather system forming in the Atlantic. But if they could complete the repairs before a storm threatened the city, no one would ever need to know how close they'd come to catastrophe. The work began immediately. Teams of welders were assembled. Massive steel plates were fabricated and delivered to the site. A careful schedule was developed to minimize disruption to the building's occupants while maximizing the speed of repairs. Every afternoon at 5 o'clock, carpenters arrived at the Citicorp Center. They built temporary wooden enclosures around the joints that needed reinforcement, blocking them from view of anyone passing through the building. At 8 o'clock, when the offices were empty and the building was quiet, teams of welders arrived. They worked through the night, welding heavy steel plates over every bolted joint in the diagonal bracing system. Each reinforcement took hours of careful work. The welding had to be perfect. Any weakness, any flaw, any gap in the new connections would compromise the entire repair. The sound of arc welding echoed through the empty building every night. The smell of burning metal, the heat from the torches, the electric buzz of welding equipment, the hiss of the cooling steel. At dawn, the welders finished their shifts and disappeared. The wooden enclosures remained in place, concealing their work. Office workers arriving for the morning never saw evidence of the frantic overnight repairs happening in the building's structural core. Week after week, the work continued. Joint by joint, floor by floor, the building grew stronger. Each welded connection took hours to complete properly. The steel plates had to be positioned precisely. The edges had to be beveled and cleaned. The welders had to make multiple passes, building up layers of metal to create connections that would never fail. Every weld had to be inspected. Any defect, any gap, any weakness meant grinding it out and starting over. LeMessurier monitored the weather obsessively. Every tropical depression forming off the African coast, every storm system organizing in the Caribbean, every weather pattern that might develop into a threat. 6 weeks into the repairs, on August 31st, 1978, Hurricane Ella formed in the Atlantic. Within 2 days, Ella had strengthened into a Category 4 hurricane with sustained winds of 137 miles per hour. It was the strongest hurricane ever recorded in Canadian waters at that time, and every projection showed it moving toward the northeastern United States. The repairs were only half finished. Emergency evacuation plans were reviewed. The Red Cross volunteers were alerted. The NYPD prepared to implement the largest evacuation in the city's history. Weather services tracked the storm every hour, providing updated projections of its path and intensity. LeMessurier barely slept. Every update brought new projections, new possibilities, new fears. The building could now withstand stronger winds than when the crisis began. Some of the most critical joints had been reinforced. The backup generators for the tuned mass damper were installed and tested. But it wasn't enough. Not yet. Not for a Category 4 hurricane. If Ella maintained its course toward Manhattan, they would have to evacuate. Tens of thousands of people would flood out of Midtown. The story would break. The world would learn that one of New York's newest skyscrapers had been on the verge of collapse. And even with partial reinforcement, there was no guarantee the building would survive. September 4th, 1978, became the most stressful day of William LeMessurier's life. Hurricane Ella was now less than 300 miles off the coast. Within 24 hours, it would reach New York. Within 24 hours, they would know if the building stood or fell. And then, late in the afternoon, something changed. The storm's movement shifted. Instead of continuing toward New York, Ella began to curve. The latest projections showed the storm turning away from the coast. LeMessurier watched the weather maps with the intensity of a man watching his own execution either proceed or be called off at the last second. Hour by hour, the turn continued. By September the 5th, Hurricane Ella was moving due north, roughly parallel to the coast, but staying well offshore. The winds that would have tested the half-repaired Citicorp Center, winds strong enough to potentially bring down the building and kill thousands of people, blew harmlessly over empty ocean hundreds of miles from land. The crisis wasn't over, but the immediate threat had passed. LeMessurier and his teams continued working through September and into October. Every joint was reinforced. Every connection was tested. By October 19th, 1978, the repairs were complete. The building was now stronger than it had been in the original design specifications. According to LeMessurier's final calculations, a storm strong enough to compromise the reinforced Citicorp Center would occur only once every 700 years. And remarkably, almost impossibly, the general public never learned what had happened. 1978 was the year of a major newspaper strike in New York City. The city's largest newspapers were shut down for weeks during the very period when the repairs were being made. Without the major newspapers investigating and publishing the story, public attention never focused on the Citicorp Center. By the time the newspapers resumed publication, the repairs were complete. The crisis was over. And with no immediate disaster to report, the story simply faded away. Everyone went back to business as usual, and the secret remained buried for 17 years. The truth finally emerged in 1995, when Joe Morgenstern, a journalist for The New Yorker, overheard someone telling the story at a party. Morgenstern tracked down LeMessurier and convinced him to give a detailed interview. The resulting article revealed for the first time how close New York had come to one of the worst disasters in American history. The revelation shocked readers, but the reaction to LeMessurier himself was surprising. Instead of destroying his reputation, his honesty enhanced it. The engineering community praised him for his decision to report the problem and take responsibility. Leslie Robertson, the engineer who had confirmed LeMessurier's calculations and helped manage the crisis, later said something that cuts to the heart of the entire story. "I have a lot of admiration for Bill, because he was very forthcoming. While we say that all engineers would behave as he did, I carry in my mind some skepticism about that." Robertson understood what most people miss. Saying you'd do the right thing is easy. Actually, doing it, when the consequences include professional destruction, that's different. That requires a kind of courage most people never have to find. LeMessurier's insurance company did something that shocked the industry. After such a costly claim, they lowered his premiums instead of raising them. They recognized that an engineer willing to identify and fix a problem before it caused catastrophic damage was a safer risk than engineers who might be tempted to cover up their mistakes. In the years following the revelation, LeMessurier gave lectures about the crisis at Harvard, MIT, and other universities. He was remarkably honest. He talked about his initial panic, his consideration of suicide, his temptation to stay silent. He didn't portray himself as a hero who immediately knew the right thing to do. He portrayed himself as a human being who made a terrible mistake, faced an impossible choice, and ultimately decided that saving lives mattered more than saving his career. In his lectures, LeMessurier told students exactly what went through his mind. "Here I am," he said, in a 1995 lecture, "the only person in the world who knew. There's nothing wrong with the building, nobody knows anything's wrong, there's no cracks, the building behaves itself perfectly. So what do you do?" The question hung in the lecture hall. His students waited for the heroic answer, the clear-cut ethical response they'd read about in textbooks. LeMessurier gave them something else, the truth. "I had information," he told them, "that if it got out, everything I had built would be destroyed. My career, my reputation, my firm, everything. And I had information that if it didn't get out, thousands of people could die. Those were my choices." He paused. Then he added something that became legendary among engineering students. "I had the power to influence extraordinary events. That power came from a simple phone call, a student asking about the corners, wind hitting diagonally instead of straight on. A question that every engineer should have asked, but didn't. For decades, the identity of that student remained a mystery. Then a woman named Diane Hartley came forward, saying she'd been that Princeton architecture student. Later, another student, Lee DeCarolis, also claimed to have made the call. LeMessurier died in 2007. We'll never know for certain which student or students prompted him to review his calculations. But what we do know is this. A young person had the courage to question the work of one of the nation's most celebrated structural engineers. Instead of dismissing that question, or becoming defensive, or assuming he couldn't possibly have made a mistake, LeMessurier took it seriously. He checked his work. He found the error. And he fixed it before it killed anyone. The structural engineering community has studied the Citicorp crisis for decades. Over 200 academic papers have been published analyzing the technical details. The case appears in every major structural engineering textbook, every ethics course, every professional responsibility seminar. Today, approximately 40,000 engineering students per year study what happened when an architecture student asked about quartering winds. The case has been translated into 23 languages. The impact extends beyond education. Building codes in 32 states were modified because of the Citicorp crisis. Review procedures changed. Inspection protocols were strengthened. The substitution of materials now requires structural engineer approval in most jurisdictions. Wind loading calculations became more comprehensive. But the biggest change was cultural. Before Citicorp, admitting a major error meant professional suicide. After Citicorp, engineers knew that honesty could save your reputation instead of destroying it. LeMessurier's reputation increased. He received awards. Universities invited him to speak. His firm thrived. The crisis proved that doing the right thing, even when it's terrifying, even when it threatens everything you've built, can define you in ways that success never could. William LeMessurier died in 2007 at the age of 81. His obituary in the New York Times mentioned the Citicorp Center first. Not his other buildings, not his innovations, not his awards, the building he almost got wrong, the crisis he handled right. At his memorial service, a former student spoke about what LeMessurier had taught him. Not about structural analysis, not about wind loads or joint connections or diagonal bracing. About being human. About making mistakes. About having the courage to fix them. The student said LeMessurier once told him, "The building code only required perpendicular winds. I did those calculations. I met the code. I could have said that was enough, but it wasn't enough. Because the code isn't what keeps buildings standing. Physics is. And physics doesn't care what the code requires. That's the lesson of the Citicorp Center. Not that engineers make mistakes. Everyone knows that. The lesson is what happens next, whether you protect yourself or protect everyone else, whether you stay silent or make the call, whether you let the building stand or make it right. Walk past 601 Lexington Avenue in Midtown Manhattan today. Look up at that slanted roof cutting across the skyline at 45 degrees. See those 4 massive stilts holding 60 stories above the street. Behind the aluminum skin, welded into the building's steel skeleton, are reinforcements that shouldn't exist. Repairs that were never supposed to be needed. A fix that saved 10,000 lives from a disaster almost nobody knows about. Every weekday, approximately 15,000 people work inside the Citicorp Center. Every year, millions walk past it on the streets of Manhattan. In the 47 years since 1978, roughly 600 million people have been within 10 blocks of the building without knowing they were standing where the evacuation zone would have been. They don't see the corners. They don't see the quartering winds that could have brought it down. They don't see the bolted joints that weren't strong enough. They don't see the 2 months of nighttime welding. They don't see Hurricane Ella turning away 300 miles offshore. They don't see the evacuation plans that were never implemented. They don't see the 10,000-person death toll that never happened. The Citicorp Center stands today because of steel plates welded in secret during the summer and fall of 1978. But it stands for a different reason too, because one engineer received a phone call from a student, checked his work, found his mistake, and refused to let pride or fear or self-preservation matter more than the truth. Engineers praised the Citicorp Tower design in June 1978. By October, one of those engineers had saved thousands of lives by asking the question nobody else asked. What about the corners? The corners had spoken. The building answered, and Manhattan never knew how close it came to falling.